Alright, and so for the last video of today, we'll do the linearization, so the tangent of that residual. So now we have this equation of the residual, and then what we want is we want to linearize that residual. So the directional derivative of the residual, which is a function of theta, in the direction of some increment theta, and we'll do it theta I. And this will become clear, well, theta I E. It will become clear what this refers to. So we have to do the linearization. So let's do it part by part. So this is what we want. And so let's do the first term, which was the integral of q. I'm gonna go back to the integral because it doesn't matter at the end. Like, we're gonna linearize on the before the discretization, and then you'll see that we can go back to the integral that we had initially. It's no problem. So we had that dotted with the gradient of the different shape functions, right? So n1, n2, n3, and n4. So this was our original term in the residual. So let's do the linearization of that. In the direction of some increment. And so if you recall the Q is, as I said, Q of theta, I made it minus K of theta gradient respect to X of theta. So I want the linearization. Notice that when we put the linearization here, so this will be equal to minus integral over the element of the linearization of Q in the direction of the increment dotted with the gradient of the shape function. So basically all I need to linearize is this one, because the shape function doesn't depend on theta, so I don't need to worry about that. So really only thing I need is I need the linearization of Q in the direction of the increment. Chain rule, so one of them will be minus the partial derivative. Actually, it's not a partial, it's just a total derivative. So minus the total derivative of K of theta with respect to theta times the increment, right, times the gradient of X. This is times the gradient with respect to X of theta. So here, just chain rule, and then multiplying by delta theta. And then that minus K theta. And then the linearization of the gradient of theta is actually the gradient of the increment. K of theta times the gradient of the increment. So this is the linearization of Q in the direction of the increment is partial of K with respect to theta times the increment times the gradient of theta minus K of theta times the gradient of the increment. So plug that back into here. So this, and note that, this is true for any increment. It's just that we want the linearization with respect to the discrete degrees of freedom. So this would be the linearization for any increment, but the reason why I have here this increment theta IE is because the way I can I can linearize is I should linearize in the direction of each of the increments of the nodes, because that will give me the tangent, which we will see in a sec. So what is this? So this is integral over omega e of linearization of this term, which we ended up saying is d k of theta with respect of theta gradient of x of theta, all of that times the increment. And here I'm explicitly saying that the increments are going to be increments for each node, plus integral over omega e of k of theta, and then I have gradient of the increment times gradient of the shape functions. And so what I'm gonna do now is how do I make these increments be described or discretized in the same way? Because if I do, hopefully this is clear. I can do maybe this is less confusing. I can do the linearization with respect to any increment. It doesn't have to be a nodal increment. I can just do it with respect to any increment. It will just look like increment of theta, right? So I just did the linearization with respect to any increment, but now what I'm gonna say is I don't want just any increment. But the increment given by the discretization. So the increment is also going to be a sum of the shape functions of the element times my increment values, because I could also do that, right? Let me use J, because I'm gonna switch to J because here I should have, and actually I'm missing a gradient here. So here it's like this. Yeah, here I'm missing a gradient of n. Gradient of ni. And yeah, okay. So I'm gonna use J because I'm already using I for my residual, right? Like the ith component of the residual has it's right here. And now I'm linearizing with respect to an increment, so I'm gonna introduce the discretization of the increment as nj. It's the same shape functions, I'm just using a different index. So now I want an increment that is specifically given by this form, right? So I want an increment discretized by these nodal values. And so if I plug that in, so plug into linearization, what you will see that I have is let's just copy this, and actually I can expand a little bit more. So I have this, but so derivative of k of theta with respect to theta times gradient of theta with respect to x times the gradient of the shape function I with respect to x times, and it should be the increment, but now instead of the increment is going to be sum of nj increment, and I put the sum outside. Hopefully that's okay. Well, let me leave it inside and then we'll put it outside. times the increment, right? The omega. Plus the second term is k theta times the gradient of the increment. So now gradient of increment is going to be not the gradient of the increment, but it's going to be the sum of, well, let me just do the gradient of the increment is the sum of the gradient of the shape functions times the increments, right? So here, instead of gradient of the increment, I'm going to have sum of the gradient of the shape functions times the increments times ni, times the gradient of ni, and that's it. So I want this now, right? So this is my linearization, but now I have plugged in this discrete increment, or the increment is discretized in the same way as my degrees of freedom. And so what do we have here? Now we have i's and j's, and we have this sum. So this is actually similar to what I did for the weak form. If you rearrange this, now what you will see is that you will have, sum over j, right, of increment, and then times everything, but now I'm just going to end up with ni's and nj's. So everything like this, but now I don't need this, I just need nj here. Nj here. And then here I also don't need sum, I don't need this, I just need gradient of nj. Times gradient of ni. There we go. Right? So now this, notice that this depends on, so now I have two indices here, right? So here I have index I, 1, 2, 3, 4. And then here I'm summing over j's, which you should think of this as the sum over j's. You can think of this as vector operation. So let me rearrange once again. And what I'm gonna do is I'm gonna put all of those increments here. So increment of the first node, increment of the second node, increment of the third node, increment of the fourth node, and then here I need the j, but now I can also choose each of the i's, right? So here it's gonna be basically each row is gonna be one of the i's, and then each column is the j's. So each row of this matrix is one of the i's, each column of this matrix is one of the j's. Obviously these increments theta 1, theta 2, theta 3, theta 4 are the j's, right? Because when we have matrix vector multiplication, you go like this times this. So basically these are, j equals 1, j equals 2, j equals 3, j equals 4. So what I need to put in here is basically what I have written up here, but I just need to replace, well, and this is definitely not gonna fit, right? Because just for this one, let's just pick a few. Let's say, what is this one right here? So that one is I equals 1, j equals 1. So that one you can see that I just need to replace 1 and 1 here. So here just replace Ni with 1, Nj with 1, Nj with 1, and Ni with 1. So overall, this would end up going up there, right? So if you calculate this, that would be one of the entries of this matrix. Obviously, this is a 4x4 matrix. This is the tangent. So let's do another one. Let's do 3, this one. So 3, 2. So I equals 3, j equals 2. So that one would be same thing that I had before. So I don't need this one. And just replace i's with 3's and j's with 2's. And that would be that entry. So overall, you have 4x4 combination for this. So typically we call this KE matrix. So that's the stiffness matrix in the standard finite element context. This will be the stiffness matrix. Here it's the tangent. Because, for example, here we don't have stiffness, right? We are doing the heat transfer problem, so this is sort of like the conductivity matrix. But in more general terms, this is a tangent, because all we did is we had a residual, which depends on theta. It might be a nonlinear function of theta, and then we are linearizing that with respect to some increment, and we are using the discrete increment. And when we plug in the discrete increment, you can rearrange things, and basically what you end up with is a definition for the for this stiffness matrix or tangent. I would say tangent. I prefer that. How do you compute these integrals? Well, the same thing as before. Loop over the integration points, and for every integration points, you have everything that you need to evaluate here, right? You have all the shape functions. You know how to take gradients. You know how to interpolate the theta. Note that this might still be a function of theta, right? So you can see here that, for example, there's still a theta in there. There's still a theta in there, but that's fine. I mean, we don't need to take more derivatives. This is all that we need, and this is basically what we need for the Newton-Raphson, right? We need our equations. So in the Newton-Raphson case, what do we need? We need a residual, which is a system of nonlinear equations. Inside of an element, I show you how you can compute it in the previous vector. And then in order to do the Newton-Raphson, we need basically the derivative of the residual with respect to the degrees of freedom. How do we do that? We can do it by linearizing, right? So we have to linearize the residual. So you can start with the statement of the weak form for the element. Then you can linearize that with respect to some increment. And then, because we want the derivative with respect to the degrees of freedom, or the linearization with respect to the degrees of freedom, then not just any increment, but an increment that is basically aligned with my degrees of freedom. So if you do that, then you are essentially taking the derivative with respect to your degrees of freedom. So when I plug in this increment, then because the directional derivative is linear, I can always plug out the increments, and I'm going to end up with some matrix times the increments. And then again, this is true for a single element. So what you will see is that, after you compute the residual for the element and the stiffness for the element, or the tangent for the element, you need to assemble into global residual and global tangent. But we'll do that on Thursday. Sorry, not without the E. So the total residual and the total tangent to do Newton-Raphson. but we'll do that on Thursday. Yeah, but hopefully this is somewhat clear. I might do a little bit of a Python script for this one. I haven't started that one yet, but yeah, all right, that's it.